All right, how's everyone doing? Nice to see all of you. Always nice. We have somewhat of a big one today. I'm a little bit worried we're not going to get through everything. I think for almost all of you, this is a bit of a review. Like, you've all seen hypothesis testing before. So I'm expecting, essentially, we're going to cover similar concepts to what you've seen before, just from a slightly different perspective. Next class, after the mini exam, we're going to start working with regression models to do a lot of the hands-on things that we're talking about from a conceptual level today. But really what I expect from you all is not just the ability to run these t-tests, run regressions, use the general linear model, but I expect you to understand fundamentally what it's doing. And if I hope for one thing from you this semester, is that you leave the class having a general idea for how we constructed regression and the t-test in the first place. So like the sort of discovery process of building statistical models. Not that you could do it from scratch. I don't think I could if someone forced me to. It's a lot of work, but at least understanding it from a high level. What are we doing when we test a model? So this is where we're going today. We're going to hopefully at least finish up with part 3, sort of introducing the basic ideas in the general linear model in the context of hypothesis testing. Like I mentioned, you've seen hypothesis testing before in your stats class, so hopefully this is either a similar perspective or offers something extra, some extra insight into what we're doing when we run hypothesis tests. A bit of housekeeping before we get in. There's no homework 3.3, but there will be homework 3.4, which will be posted right after class. So take a look at that. As always, if you need an extension, feel free to take it. Just let me know that you're doing it. And then mini exam 3, which covers these things, which will feel, I think, most similar to homework 3.4. Now that by the end of class, we will have covered this stuff. It'll cover the concepts in in part 3. So just as always, I'll post a mini exam demo for you. I think these are nice, so let me know if you like it. And then I think you told me you'd be interested in a review session if I'm able to pull that together. Is that a yes? Still interested? Okay. So I think by the end of class today, we'll be in the ballpark of completing, sort of putting a bow on some of these ideas in a way that we can actually work with. Okay, so we've done a lot of like simulations and sampling. The reason we're not just talking through these ideas at a high level is because I want you to feel the intuition for what's going on behind the scenes with these things. The big question for today, how do we learn about, we've been sort of creeping up to this question for a while now. How do we learn about the population when we don't know anything about it except the sample? So I'm just going to draw a sample. I don't know mu, and I don't know sigma. What do I do? Each of you are going to face this question in your final project. It's part of the requirement for your final project, is that you approach a question of this type. Yeah. Yeah, so we're going to use sample data to make claims about the population. We don't know mu and we don't know sigma, so we're going to use the sample, which is the only thing we observe. Every class for the last 2 weeks, I've come exclaiming the profundity of this idea that we can actually do this in the first place. And what we're going to do today is kind of put a bow on those conceptual ideas. So that's our big question. Just as a refresher of the sequence that we've been working through, in 3.1, we talked about what happens if we did know a random variable. And we talked about different things we could do if we had random variables. All kinds of probability questions. Then in 3.2, this is where we started leaving the world of knowns. So we talked about sampling and unknown random variables. And this is where we started introducing the ideas that the sample mean, according to the central limit theorem, approaches a normal distribution with some shape to it. And it's centered on the truth. These are such important ideas. They really form the building blocks of everything else we do in the class. But even in 3.2, we simulated this with die rolls. You'll remember that? So a week ago, I had you roll a bunch of dice, not dies. And this is not Game of Thrones. Okay. I have a PhD in economics, not stand-up, so give me a little credit. We drew a bunch of samples. We looked at the distribution. I asked you for increasingly large samples, and then we plotted the distribution of sample means. And as we increased the rolls of the dice, the distribution of the sample means got closer and closer to a normal distribution. And then at the end of that class, I plotted the distribution of like 1,000 die rolls. And it turned out this is what we know from the central limit theorem. So this is a simulation showing a mathematical result. Then last class, we introduced this idea of a confidence interval, where if we knew the standard deviation of the population, so if we knew sigma, we could then just construct a range where we knew, given some level of confidence, that our sample mean would be, if we drew it from the population, it would live within that interval. So a confidence interval tells us how confident we are that a sample mean will fall on some interval around the truth. And this was pretty nice. This was sort of our first step towards systematizing this idea of measuring the closeness between the sample mean and the population mean. But this was not enough, and this was not enough for two reasons. We can use this. We can construct confidence intervals if we know sigma. But like I mentioned, I think at the end of class last time, in general, we're never going to know sigma. Part of the thing we're after is to use the sample to construct everything in the test. Like, we don't want to go into the test needing to know something about the population, because that's precisely the question we're after. How do you know something about the population? So requiring there to be a sigma is not okay. So we're going to build a model that allows us to not need sigma. The second thing is that when we construct confidence intervals, the way we've done it, the way we simulated it a week ago, is the distribution of sample means followed, the sampling distribution was centered on the truth. And in general, we don't know the truth either. We don't know the population mean. So the first thing we're going to talk about today is how we get away from needing mu and sigma. And then by the end of class, I'm hoping we will, if we move quickly enough, if I talk fast enough, we'll get through this with plenty of time. How do we test for the truth if we don't know mu or sigma? Okay, so essentially where we left off last time is when we didn't know mu, the population mean, but we did know the sigma, the distribution of the standard deviation of the population. What we do know is that the sample mean approximates a normal distribution with this standard error. So you remember, the standard error is not the distribution of the population, but it's the distribution of the sample means. And we talked through where that square root of n comes from. I just toss this equation out to you without a lot of justification, but you may have seen some of the intuition for this. As the sample size gets larger, the variability just gets smaller. And so we can show this mathematically that it must be the square root of n as the sample size grows. So as the sample size gets larger, the standard error, the variability of the sampling distribution, gets smaller. And each time we draw a new sample, that sample is different from the last one. This sounds like so obvious, but I think this is sort of underappreciated. So we're going to keep coming back to this. So we asked this question in a certain kind of way. What do we do when we don't observe mu? But today I want to show you some pictures and some justification for this measure of closeness. So last time we talked about centering the sampling distribution on the truth and then looking at how far away our sample mean is from it. But today what we're going to do is sort of flip this and look at it from a different perspective. So here are the two perspectives. The first one is that we can look at, this is what we've done so far. When we rolled a bunch of dice, the distribution of the sample means was centered on the truth. So anytime we draw a sample and calculate its mean, we can find, using confidence intervals, we can find how far away that x bar is from the truth. We can check whether our x bar is within a confidence interval that's centered on the truth. And this is how we did the probabilities last time. So we walked through some random variables, and I asked you some questions about how far away certain things were, using the knownness of the sampling distribution. But this is not going to work for us, right? How do I calculate a confidence interval that's centered on the truth if I don't know the truth? Does anyone know what we do here? I know someone mentioned this actually last class. Anyone know what the second perspective is? How do we construct confidence intervals if we don't know the truth? Which is like precisely our question. Well, if we know sigma, we know how wide the confidence interval is. So instead of asking, is x bar within a confidence interval around mu, we can ask, is mu within that same confidence interval, but centered on x bar? So if we know sigma, we know what the standard error is. So we can just sort of flip the perspective. So I'm just going to plot it out like this. So instead of centering the sampling distribution on the truth, we're just going to flip the question and ask, is mu within the confidence interval centered around the truth? Sorry, centered around the sample mean, x bar. And what I'm going to try to prove to you is that these are the same question. Either way we look at it, it's an identical question. If the answer to the first question is yes, the answer to the second question is yes. And if the answer to the first question is no, then the answer to the second question is no. The reason this is important, kind of like if this weren't true, we couldn't do this. We couldn't do hypothesis testing. The reason this is important is because we can then ask questions about how far away any guess we make about the truth, how far away that is with the relative to the sample mean. So my claim is this: if x bar is in the confidence interval around the truth, then the truth, the population mean, will be in the confidence interval around the sample mean. So just to give you a picture of this, I ran a bunch of samples. So these are, what's this? Is this 100 samples? I actually don't remember the name. Looks like 100. Might have been 50. A bunch of samples. This first row, I've just gone through. So the truth here This is our running example from last time with wait times. The true wait time, the population mean wait time, is 12 minutes. And then I've run 100 samples. These little observations I've put in green, sometimes red. And then I've constructed a 95% confidence interval around the truth. And then just asked, for each one of these 100 samples, is that sample within the 95% confidence interval? So this is sort of similar to the simulation we ran last class, where I asked you for a sample mean, and then we checked the confidence intervals. But what I've done here in the first row is just construct the confidence intervals around the truth, and then check each sample whether it falls within the confidence interval. If it doesn't fall within the confidence interval, I've colored it red, just so you can see it more easily. So here you can see the sample mean has a much higher wait time than the truth. So it's outside the 95% confidence interval. This shows us two things. One, not just like we talked about last time, not every sample we draw will be within a 95% confidence interval of the truth. And in fact, what's this, 5 of them? No, 6. 6 of my 100 observations fall outside of a 95% confidence interval. So roughly 95% of the time, I'm seeing data that's very far away from the truth. It's like outside of my 95% confidence interval. This happened 6 times in this sample. And I would predict it would happen 5 times if we ran a bunch of samples. So confidence intervals give us some level of confidence, but it doesn't mean that we're close with certainty, right? Like that's the entire point. So, this is a probabilistic statement. But second, let me show you the line below. So instead of centering the confidence interval around the truth, what I'm doing in the second row is centering the confidence interval around the sample mean. So these are the same confidence intervals. It's just I've centered them on the sample mean instead of the population mean. And what you can see is each time the sample mean falls outside of the confidence interval around the population mean. So each time one of these things shows up as red, this also shows up as red, telling us that the population mean falls outside the confidence interval when we center that around the sample mean. So if we shift perspectives, center the confidence interval around the sample mean instead of the population mean, the answer to our question will be the same. And fundamentally, maybe you can see why this is true. That all we really care about is the difference between mu, the population mean, and x bar, the sample mean. And the confidence interval just gives us some measure of distance between these two things. It doesn't matter what the center point is. But the important result here is that we can center the confidence interval around the sample mean and then make claims about the population mean without needing to know the population mean. We don't need to know what the center point of this distribution is to make claims about the distance between any guess we make about the truth and our sample mean. Any questions here? Okay, so if the sample mean, x bar, is within the confidence interval around the truth, then it's also true that the truth is within the confidence interval centered around the sample mean. And this gives us leverage over making claims about the truth, because if we can construct a confidence interval, we can then test probabilities for how far away our guesses are from the truth. And this gives us some leverage over answering inference questions about unobserved populations. Okay, so these two things are mathematically equivalent. I think this is a cool picture. Anyone else like this? I asked you for like whether you liked my figures at the beginning of the semester. You remember that? We're now in the ballpark of like maybe they're all bad. No, I like this one. I think this is a cool way of presenting the data. It's mathematically, these two things are mathematically equivalent, which gives us leverage. Okay, so this is all with an unknown population mean. So this is what we call the sampling distribution. I haven't used those terms in class before, but this is the sampling distribution. It's the distribution of the sample means that's centered around the truth. But now we can shift it so that it's centered on, like we've constructed it, we know what it is, so we can just center it on the sample mean, even though what the central limit theorem gives us is that it's centered on the truth. Because all we really care about is the difference between mu and x bar. Okay, so this is how we construct confidence intervals. And this is just the idea where before we had it centered on the truth, now we're centering it on the sample mean. And then we can just check how far away any guess we make about the truth, whether that falls within some confidence interval. So it has the same shape, just a different reference point. Okay, so as we start working our way closer to building statistical models using what we call ordinary least squares, I want you to start thinking about the data, these x bars, on the vertical axis. You could think of this as a y bar if you like. The standard notation for univariate data is x, but I want you to start thinking about these things on the vertical axis. So this is the first picture in that direction. So this is just another way of showing the thing I just visualized for you before. But how close are the sample mean and the true population mean? Each time we randomly draw, we get a different x bar. We also get a different sample standard deviation, which is something we're going to spend, I think, most of class time talking about. We're going to talk a lot about S. So what I want to show you here, and I wanted, we don't have enough time to do this, but I wanted to actually have you calculate some of these samples. But what I'm going to do instead is just show you some samples I drew on screen. So from wait times, we know what the truth is, but it's unobserved to us. But if we did know it, we could just check whether it falls within a confidence interval. So this is just a sample. You can see the sample in blue. And then through the central limit theorem, I know what the theoretical distribution of the sample means is, what we call the sampling distribution. And all I've done here is just drawn the sampling distribution around the sample mean. So all I did was take a sample, calculate the sample mean, x bar, and then center the sampling distribution on x bar. And I did this for each one of these samples. So the first thing to realize here is that each one of these samples looks slightly different, right? Like the sample mean moves around a lot. And so you can see the sampling distribution, when we center it on x bar, also moves around a lot. So what this also means is that the confidence interval moves around. So our confidence interval is moving. That's where the randomness comes from, is the sample. The truth never moves. And this is going to be important later. So we'll come back to it. The second thing to realize here is that each time we draw a random sample, the sample standard deviation, S, also is different in each one of these samples. So for this first one, I have S is equal to 2.9. The second one is 3. So obviously, that's a different number. So the variability in the first two samples is different. And then you can just compare each one of these samples, look at the variability, like the spread in each one of these samples. This is going to be very important, that the variability in the data is itself variable. Okay, so we have differences in the center point moving around the sampling distribution. which also moves around the confidence intervals. But we also have movement in the sample standard deviation. Okay, so this is all really nice. This is how it should be. But and then we can perform our tests. So here we've constructed a sample, and then we can test whether 12 is within our confidence interval. And we'll come back to how we do this more formally a little bit later, which you've probably all seen, like null hypotheses and such. But the important thing to remember here is that when we construct these confidence intervals, when we're constructing the sampling distribution around our X bar, we're assuming that we know sigma. But in reality, you're never going to know sigma. In fact, that's going to be a big part of the challenge. I don't want to overstate that, actually. We're going to have a really simple way of getting around this problem. But there's a theoretical reason why, or maybe a practical reason why we can't just do it this way. And that's because we don't observe sigma. So you're going to be presented with an environment where you don't know sigma, and then you have to do something about it. So each one of these confidence intervals assumes that we know sigma. But for the rest of the semester, we're going to assume that we don't. And this is the true sort of working environment. Okay, so what I've done here is just plotted out, I took 1,000 samples with a sample size of 15, and then plotted out the distribution of the sample standard deviations. And we have some variability here. I showed you a picture much like this last time. So what we did last class, or I guess sort of this class, right, is we switched the center point of the sampling distribution. It's like our best guess in some sense of the truth is to use our sample. Here, what if we simply switched the sigma, so the population standard deviation, what if we just swapped that with the sample standard deviation, S? We can see that there's a ton of variability here. Anyone know what happens? So we centered the sampling distribution on X instead of mu. What would happen to our model if we swapped S for sigma? So we just said, okay, we know we need a standard error for the sampling distribution. What if instead of using this unknown population, we don't know what it is, the unknown sigma, what if we swapped that in the standard error? So the spread of the sampling distribution. What if we swapped it for S? It's like our best guess is just the variability in our sample. Let's just swap the variability in sigma. What if we just guess that it's equal to the variability in our data? Anyone have an intuitive idea of what happens when we do that? You're like, all right, so I look at my data, I look at the variability in like wait times, for example, and calculate the standard deviation, which is something we did last week. And we just replace this unknown parameter, sigma, with the thing we can actually calculate. And then we can construct the normal distribution to get our sampling distribution and construct confidence intervals that way. Do you think this would be the right thing to do? I think you know that it's not, probably by the framing of my question. Let me show you what happens when we do this. So I just want to give you an intuitive sense of why we can't just swap the sample parameter for the population parameter. We can't just use our sample, like the thing we calculate, as a guess. It's our best guess in general, but it's not a perfect swap for the truth. And here's why, specifically in this case. I don't think we have enough time to do this exercise, so I didn't pull this together for us today. What I want to do instead is take you through me running these samples on my computer. If you wanted to build this up for yourself, maybe I'll post this after class. But I'm going to run a bunch of simulations to test what happens if we swap the sample for the true standard deviation in the sampling distribution. And I'm going to show you that we make a really big mistake. Not a big mistake, but we'll make a mistake. We'll be too confident. Okay, so our question, will a 95% confidence interval using S, so the sample standard deviation, replacing sigma, will that confidence interval correctly contain 90% of the population means? Maybe a better way of saying it is, will the confidence interval correctly contain the population mean 90% of the time? The answer is no. And I'm going to show you why we can't just swap these things and give you an intuitive sense for why. So this is, I think, the first picture of why. Do you like this picture? No? I spent like 30 minutes on it. So I think in general, these kinds of pictures are easier when you have someone describe them to you. Yeah. So let me just walk you through, and maybe you'll like it better afterwards. Wow, 30 minutes down the drain. Oh my goodness. No, this is a great figure. So this is 7 samples. I collected from the wait times. I have the theoretical distribution of wait time. So I just did a bunch of sampling, much like we did with the die rolls. Except here I took samples of sample size of 5. And then what I'm doing is we're going to go back to centering the sampling distribution on the truth, on the population mean, just so I can show you a better picture of the variability in the sampling distribution if we simply swapped S for sigma, if we swapped the sample standard deviation for the population standard deviation and used that to construct our standard errors. So what you can see here is in this first sample, we have a sample standard deviation of 2.5. The sampling distribution, when we center it on the truth, looks like this. But this is a different sampling distribution than what happens when the sample standard deviation is larger. So in the second one, you can see the data is more spread out. Looks like this is cut off a little bit, but you can see there's more variability in the sample. So what this means is the sample standard deviation is larger. And because the sample standard deviation is larger, when we replace that larger sample standard deviation in place of the population standard deviation, sigma, the sampling distribution gets larger. So just like the means move around in each one of these samples, the sampling distribution will move around if we're simply using the sample standard deviation as our guess of the population. So you can see each one of these has a different distribution. It's differently spread out. And that's simply because we're using our best guess, which itself is variable. This is a problem, and I'm going to show you why this is a problem. So this impacts our confidence intervals. So if I were to construct confidence intervals using these sampling distributions, they would be different for each one. So our confidence intervals themselves would be variable. And that's not something the normal distribution or the central limit theorem allows us to do. So this is the thing I was going to ask you to do, is to simulate many samples and then check how often the 95% confidence interval contains the population mean when we do this swap. But I'm just going to show you a picture of what happens when we do this like 1,000 times. The important idea here is that swapping in S for sigma introduces a second layer of variability. We have the variability in X bar. When we swap in S for sigma, this introduces a second layer of variability. And that kind of breaks our model. So here's a picture. We talked a bit about the t-distribution. We're going to come back to this in a second. But I ran, I think this is 1,000, it might have been 10,000 samples. The sample size doesn't matter here, but it was with 15 observations. And what I did is swap, because we're assuming that we don't know sigma, I swapped in S in for sigma when I calculated the confidence intervals. And I calculated a 90% confidence interval. So I constructed the 90% confidence interval around the sample mean and just checked how far away the truth was. So I just measured the distance between the confidence, between the X bar and mu, and then just checked whether they were close according to the confidence interval. And when I did this, I would expect 90% of the time, right? This is what a confidence interval is doing. It's saying 90% of the time, the truth should be close to the sample mean. But because of this variability in the sampling distribution, each one of these has a different confidence interval. So when I use the S in place of sigma, I actually don't correctly estimate the probability of X bar and mu being close. Turns out this should be 90, but it's actually slightly less than 90. It's not off by a lot, but it's off by enough that when we're doing anything with trying to understand the truth, trying to estimate an unknown population parameter, like if we're trying to estimate anything important, being off by 2.5% can truly matter. Like you don't want this as your theoretical backbone. This is wrong. And the reason it's wrong is because we have two sources of variability, one from the sample mean and one from the sample standard deviation. And they interact in a way that leads us to make systematic errors. So we can't just swap out sigma for S. This is not a econometrics class. If it was, I'd have you prove that the t-distribution, first I'd have you construct the t-distribution, and then I'd have you prove that it fixes our problems. But the t-distribution is a way of adjusting for this extra level of variability that comes from swapping sigma for S. And this is a picture, so this is the same set of samples, except instead of constructing the confidence intervals using the normal distribution with the sample standard error, which gives us a mistake, I use the sample standard error with the t-distribution. And the reason this matters, let me show you what the t-distribution looks like. So this is, degrees of freedom is just a way of capturing the sample size of the, it's a way of telling the t-distribution how confident we are in the variability of the sample standard deviation. It's not a big deal for this class. After this class, we're never going to use it again. It'll all be done automatically for us with a computer. But the degrees of freedom just tells us how spread out is the sample standard deviation, how large our sample size is. So what you can see is when we have small samples, our degrees of freedom will be very small. So a very small sample size of 3, we have you don't particularly need to know this, but sample size of 3 gives us 2 degrees of freedom. It's like 1 less than the sample size. So this is much more spread out, or maybe slightly more spread out than the normal distribution, which is in this dashed red line, which maybe you also dislike this figure. This one did not take me 30 minutes. This was a lot quicker. But you can see, when we have a small sample size, there's a lot of variability in the sample standard deviation, which means the t distribution has to be less confident, more spread out than the normal distribution. But as our sample size gets larger, the variability in the sample standard deviation gets smaller, and the t distribution gets closer and closer to a normal distribution. So the t distribution is very similar to a normal distribution. It just allows us to correct for this extra variability, this extra possibility of being wrong, by giving us less confidence. And it turns out that's exactly the right level of confidence to be for our confidence intervals to be correct. So the t distribution is spot on. We would expect 90, and we got 90.3. And if we increase this to like 10 quadrillion, this would be almost exactly 90. Maybe off by some epsilon. Okay, so using a normal distribution makes us too confident. We would expect 90. Like a 90% confidence interval should contain 90% of the samples. And it doesn't. It contains less than that, which means there are samples that are falling outside of our confidence intervals. And the reason is this picture. I want you to think about this picture. This is many different shapes to the different sampling distributions, which means we cannot use the normal distribution because it's too confident. It misses. It should be 90, and it's less than that. We're too confident when we swap out S for sigma in the normal distribution when we're constructing our standard errors.
Right.
Yeah, Savi?
Right. When you talk about too confident, you're just saying that the confidence interval is larger than what it should be with normal distribution.
It's too small, actually.
Oh, right, sorry.
Yeah.
Okay.
Yep. So it's like the confidence interval is too small when we use the normal distribution. What we actually want is for the confidence interval to be wider. If it's too small, the truth and the sample mean are not close as much as we would expect. And that's because the spread of the distribution is moving and the location of the distribution is moving. Okay. So then we correct this with this. This is like if you're interested in this stuff, the t distribution, you have to take a ratio of 2 random variables, and then you take the square root of this chi-square random variable, which gives you the t distribution, which weirdly looks very similar to the normal distribution as n grows. You take the limit of that square root of the ratio of 2 random variables, and that approaches normal. But that's not something you need to know for this class. Okay, any questions here? Okay, so this is all, we have a lot of tools. One of the problems I often see is people being very comfortable using tools without actually understanding what they mean. This is the source of the problem. We want to understand something about the population. Like we have a data set, it's a sample from a random variable, and we want to know something about that random variable. We don't see mu or sigma, so this is what we do. These are the problems we encounter along the way to construct a test. So the sampling variability in S looked like this when we had a sample size of 5. But just to show you what happens as we increase our sample size, the sampling variability gets smaller. So the distribution of sample standard deviations gets tighter and tighter. So you'll see there's less difference between these distributions as the sample size gets larger. And that's simply the same it comes from the same source as the central limit theorem. So this is to show the convergence of the t-distribution to the normal distribution as the sample size grows. So as the sample size grows, we get tighter and tighter around the truth. And the variability between these distributions gets smaller. Yeah, I guess I took out I had another figure for you, but I think for the sake of time, we're not gonna cover it. Okay, so this is the idea, right? We don't know mu, so we center the distribution on our x bar. We know what that distribution is if we did know sigma, given to us by the central limit theorem. But we don't know sigma, so we can't use the normal distribution. Instead, we use the t-distribution, which accounts for that extra variability in the sample standard deviation, which throws off the correctness of our confidence intervals. When we use the t-distribution, we get a correct confidence interval around our x bar, which then allows us to make claims about where the truth is relative to our sample mean. This is an amazing thing to be able to do. We're like going through this in class, and I talk to my friends about this outside of class. Most of my friends have seen the central limit theorem before, or at least some of them have. I think it's like, I think most people don't recognize how powerful this stuff is, including my friends. Maybe I should get new friends. I'm not doing that. Love my friends. Okay, so this is how we end up in a world where we can build models without needing to know sigma or mu. And this allows us to make claims about an unobserved population mean without needing to know anything about the underlying population. So here's sort of maybe the crescendo of the things we've been doing the past couple of weeks. This isn't the theory for how we build the model itself. We're like inching our way towards it. But this is how we run these kinds of tests. This is a claim we could ask. This is, we've been talking about wait times. You all told me you were tired of talking about Starbucks, so this is not a Starbucks wait time. This is a restaurant wait time, let's say. I get antsy when I wait 10 minutes. That's a me problem. Is our data consistent with this claim? This is a kind of question we can ask. And it's the kind of question I'm going to ask you on the homework. Is the data you're seeing consistent with a particular claim? We're going to formalize this. You've all seen this, like null hypotheses and such. This is what we're working our way towards. The population average wait time is 10 minutes. That's a claim. We have a data set. We don't need to know the truth before asking this question. All we see is our data. How do we deal with that? Okay. We're going to, instead of like knowing where mu is, we're going to ask a specific, this is what we're doing, we're asking for a specific value of sigma. Okay, so I just have a couple of things on the screen here. We might actually be ahead of schedule, I'm not entirely sure. We're actually going to try to implement some of these tests we're not going to use any fancy statistics, statistical packages. We're not going to run a t-test. We're just going to use like CDFs and standard errors and the things that we've been talking about to be able to construct some tests of particular claims. So let's say this sample standard deviation is this, so S is equal to 2.5. To calculate the sample standard error, before we've been constructing standard errors using sigma, but here we're swapping S for sigma. So our standard error is this value. And what we're trying to do, remember, we don't have to pick a particular location for the center point of the sampling distribution. So what I'm going to do is center the t-distribution on our particular guess. So we're saying we're in a world where we're expecting our null hypothesis, our mu0, to be 10. So we're going to center our sample standard deviation on that truth, or on that guess. And then we're going to check how far away our sample mean is. So we have a sample mean of 10.85. Is that consistent with a guess of 10? We're going to guess that the average wait time is 10 and check whether our data is consistent with that guess. So we center the sampling distribution on the guess and then find confidence intervals and check whether our sample is close. So here we have S. We know what N is. We have a sample size of 30. Looks like I didn't put that in the slides. But we have a sample size of 30, so we can calculate the sample standard error, which is just the variability of the sampling distribution. Okay, and then this is just some code to be able to do it. So we have S, which is our sample standard deviation. We have N, which is our population, our sample size, and then we have the standard error, which is just the ratio of S and the square root of the sample size. Okay. And what do we get? Well, if you run that computation, like I did in this code here, you get 0.56. So maybe a comprehension check question for you. Have you said anything to your neighbors yet today? I don't think I've asked you to. Tell your neighbors something fun you're doing this weekend, and then tell them the interpretation of this standard error. What is this standard error doing? What does it mean? You don't have to use fancy words, just say something about what it tells us. You're a stat major?
Double major, stat and econ.
Nice,
and
love that.
Trying to, in my academic career, by also contemplating another major.
Nice. I had 3 majors in college. So
20 years.
4.
Did it all overlap?
Yeah, that's the only way it's possible.
Oh, okay. Because stat and econ overlap with Leo, but I'm trying to sneak in something that's related.
Nice, good for you.
Yeah, because everyone is because that's like a lot of music stuff. I guess I'm a music major. I'm like stat econ.
Nice.
Stat econ. So I don't know. But I also don't want to do a 5th year. But
Yeah.
I'm kind of asking. Well.
Okay. Someone tell me a fun thing you're doing this weekend. Yeah. Okay, that's fun. Can I tell you something? Can I tell you a secret? I've been at Pitt for 9 years, I guess. I've never been to a Pitt football game. Boo. Okay, someone tell me a sort of non-technical, intuitive description of what this standard error is. What does it mean? I mean, it's maybe a tough question. The standard error gives us something about the variability of the sampling distribution. It tells us our sort of best guess about the spread of samples. That's what the standard error gives us. And then this is the sample standard error. So this is just how spread out would we guess the t distribution to be. Okay, any questions here? All right. So the next thing we're going to do is construct what we're going to call a t distribution. And we're going to talk about critical t values in a second. But the first thing we're going to do is just, so on this picture, like I mentioned last class, whenever I do these things, I start with pictures. I'm going to ask you for pictures on the mini exam. You're going to draw pictures. And then from the picture, you can then talk about your claims. We do this in every area of economics. Like I talk about this too in like intro micro. I always build a model with a picture, and then I answer the question using the figure. So here, what we're trying to do is check whether our sample mean falls within some confidence interval around our guess. So what I'm doing here, we constructed the sample standard error in the last slides. If the true mean is this, our distribution is centered on that true mean, and we want to find confidence intervals centered around 10. So this is the sort of the notation for the distribution using a t distribution. This is x bar follows a t distribution. This subscript is just telling us the degrees of freedom. This is the center point, so the middle as we're building it, and then this is the variability of the t distribution using the standard error. So it tells us how spread out this t distribution is. This is something to know. You don't have to memorize it, but a 95% confidence interval with the t value has what we call a t value. We'll talk about t values in a second, of just over 2. But we can skip knowing those things and just go directly to finding the confidence interval. This is a class we rely on code. We don't have to check these tables at the back of our textbook anymore. So Python gives us the stats package. We can use the t distribution and then just find a confidence interval that contains 95% of the data. And then this thing, the degrees of freedom, we just use the sample size. So we put in the sample size of 30, and this will give us a confidence interval. So it gives us, much like we used the ppf command from last time, we can use this interval value to give us the confidence intervals. Okay, so this is just, I ran this code. You can, it's in the slides, you can use it yourself. What I did is I just constructed this confidence interval around 10. So these numbers, a 95% confidence interval, using what we know here, gives us this value. So here's my confidence interval. And just visually, you can tell our sample mean, our observed sample mean, is 10.85. And that falls within these two numbers. So our level of, at a 95% level of confidence, we know that the sample mean is within that within that confidence interval, which tells us that our sample mean is pretty close, at least at this level of confidence, is close to our guess. These two things, I want you to be thinking about closeness when you think about confidence intervals. Okay, so our observed sample mean is within this interval, so it's not really surprising, at least with this level of confidence, if 10 were the truth. So if 10 were true, we would expect to see a sample mean like we do, at least at this level of confidence. Okay, but the idea is if our sample mean falls outside of this confidence interval, then we're confident that it's the sample mean, the null hypothesis is not generating the data that we're seeing. So if the sample mean is not close to our null hypothesis, then we're very confident that is not the truth, that the null hypothesis is not the truth. It's what we call very surprising, exclamation point. Okay, so what we're going to do here is formalize this set of ideas about this closeness. We have the sampling distribution and the closeness. We're going to formalize these ideas and talk about what we call a p-value, which you've all seen before. P-values, I have a whole rant we can go on about p-values. But for now, we're going to keep things generally pretty focused on p-values. We're going to talk about a t-distribution in a second, or a t-test, t-statistic in a second. But let's just do some definitions. So the first one is a null hypothesis. So in our example we were walking through, the claim we were trying to test was whether a wait time of 10 minutes was consistent with our sample. With our sample mean, which was 10.85. So is 10 consistent with our sample mean? So this is what we call a null hypothesis, what we're using as mu0 from before. It's a specific claim we're trying to test. We have an alternative hypothesis. You can call it either one of these things. This is the thing we, I guess I sort of don't like this terminology here. Who wrote these slides? This is the thing we sort of like default to if we can't reject our null hypothesis. We're going to talk more about how we think about these things in a second. So this is like the alternative to the thing we're testing. It's like the opposite, which is in this case that the mean is not 10. So then this sort of approach we're taking, what we call a testing approach, is essentially calculating how surprising our data is if our null hypothesis were true. And it's this level of surprise that we're going to formalize in a p-value. Okay, so p-values. There are lots of ways of measuring closeness and tests. We're going to talk about a t-statistic in a second. But the main measure of closeness we're going to use. So the p-value, just a definition before we get into some of the intuition, is this idea of measuring, seeing something as extreme as what we're seeing in our sample, given the null hypothesis. So we're saying, what if the wait time was 10? How likely is it that we see something as extreme as our sample mean, 10.85? So it's something as extreme or greater. So a little example here, our null hypothesis that we worked with was 10, and then our sample mean was 10.85. So then the question is, how likely is it under the sampling distribution to see something like X bar or more extreme? Assuming that the true mean is 10. So we're going all in on our null hypothesis, centering the distribution around the null, and then checking how much of the tails is beyond something like 10.85, our sample. So a picture of this looks like this. So we're saying, how likely is it to get something like X bar or greater, and in both directions? We're really only going to do tests like this, where we have two tails. In your stats class, you may have seen the distinction between one tail and two tails. Here, the default, just in basically every area of science, is to use two tails. So what we're saying here is we want to find the area under the sampling distribution. And remember, this is a t distribution because we don't know sigma. So this is a t distribution centered on our best guess, or our null hypothesis of 10. And then we're going to use our sample mean in green, and then look at the area under the sampling distribution, this t distribution that we've constructed. We're going to look at everything under the tails in both directions. So we have to calculate this value below, which is just, we can calculate the difference between 10 and 10.85, and then just look that far in the other direction. And then we find the area under the tails. In this case, our p-value is 0.78. So this is what's the probability we see something as extreme as 10.85 given the null hypothesis of 10. And the answer to that is it would be pretty surprising if we to see what we do see if that were true. So there's a bit of code here. This is just the CDF of the t distribution. And then I've calculated this thing. This feels a little out of order, but we'll come back to t statistics in a second. This gives us, so this is the difference between mu and x bar, and then we're just going to divide by the standard error to get a t statistic. So it gives us everything under the distribution, like we've done with CDFs, that's below this value. And then we just want it twice. So we want one for the lower tail and one for the upper tail. So we multiply by 2. Okay, so the interpretation, any questions about this? I'm sorry, this may feel like we're rushing a little bit. You'll get some practice in the homework doing these kinds of things. Any questions, though? Okay, so if the truth was 10, what's the probability that we would see something that we do? That's the p-value. That's what the p-value tells us. We would see something this extreme, this far from 10, roughly 7.2, that should be 7.8% of the time. Wow, who wrote these slides? So if this makes you uncomfortable, if this feels like we shouldn't be, like, this feels very far away. Like, I'm very surprised to be seeing something this far away from my guess. That's what we call rejection, or critical values, or critical regions. We say if the p-value is less than 5% or 0.05, we say this is like too far away for our level of comfort. So it's this is what we a general cutoff point. We need some way of cutting these things off, and this is the one we generally arrive at. We don't have time for this, but there's a real problem in science right now with p-values. We'll talk about it's sort of like when the light is about to turn red, you like gun your engine to get through. There are ways of like manipulating these things. When we have cutoff regions, we end up with problems in science. Lots of things just under 0.05. But here we don't see a p-value below. So at least at this level of confidence, we don't reject our null hypothesis. We say they're generally kind of close, or they're not too far away for us to be confident that they're not the same. I've used a t-statistic a couple of times, and it's actually what I've used here in this in the code. But the reason we use t-statistics, at least in these kinds of situations, it measures essentially how many standard errors away from your guess is your sample. How many standard errors is different between your null hypothesis and your sample mean. So the way we calculate this looks like this. So this t value is just on top we have the difference between the sample mean and our guess. And then on bottom, we have the standard error. So these are all things we know. We know x bar, we've guessed mu0, and then we can calculate what's in the bottom. In fact, we have all these numbers, so we can just plug them in. But intuitively what this is doing is measuring how many standard errors these two things are from each other. Like what's the standard error that, the number of standard errors between our guess and our sample mean. And that matters because we're trying to measure how far away these things are from each other. So I just plugged in some numbers. This is just an example of, I think I have you doing something like this on the homework. But here we have the sample mean, which is 10.85, and then we subtract off 10. So on top, we just have the like on the horizontal axis, how far apart these two things are. And then on bottom, we have the standard error. So we've actually already calculated this. And this tells us that the difference between the x bar and our guess is roughly, it's just less than 2. So it's like if you put on the horizontal axis standard errors, you would see that our guess is just less than 10 of those, 2 of those away. So it's like how many standard errors away are these things? And here it's 1.86. So this is the number that I computed. See how these sort of feel a little out of order? Blame it on my slide writer. This is that measure. We have the standard error, and then we have the difference. And the t statistic is taking, the t distribution is taking that and calculating the area below it. Okay. So I guess we're right out of time. Take a look at this. There's not a whole lot left to cover, but this is just an example and some code, and then a basic decision rule for whether we reject or confirm or don't reject our null hypothesis. Can I, there's some other slides about like how to interpret and how not to interpret p-values. Can you take a look at those? It might be of some use for the interpretation of p-values on the homework. This is the basics for univariate general linear model. What we're doing, we're going to spend a little bit more time with how we actually do these tests. This is the way you're familiar with, but I'm going to show you a much simpler approach using what we call a regression. And that's where we're going next class. Maybe I'll be able to schedule a review session. I think that would probably be helpful with this kind of material. So I'll let you know if and when that gets scheduled. The mini exam demo is definitely getting posted, so that'll be up. Don't do too much work for me this weekend, but I'll make sure you get in your homework. I'll see you on Tuesday. Sabi, how's it going?
How are you?
Yeah.
So for the p-value, we considered less than being 5%. Does that mean that the confidence level is 95%?
Yeah. So that's the idea.
Okay. And the next thing that I want to ask